Well, in this class, what we were discussing in the last class, that we were looking into the Gram-Schmidt orthogonalization technique. This technique is in use rampantly for the orthogonalization and orthonormalization of independent set of vectors, which will later on simplify the calculation calculation complexity of any other vectors, which will be expressed as a linear combination of all the independent set of vectors. So, we will continue with the Gram-Schmidt orthogonalization technique for that. So, what we have done in the last class, we considered a set of independent vectors h1, h2 up to hk, where in a k dimensional space, and we would like to constitute a set of vectors e1, e2, e3 up to ek, where each of these vectors in the target set, we call that E set as a target set. In this target set, all these vectors will be independent as well as they are mutually orthogonal and orthonormal. So, we have formulated the first element of the E set, the target set E1. E1 is nothing but H1 divided by norm of H1, ensuring that the E1 will be having a norm unity, and we have already proved that. Now, in this class we will be formulating the other elements of the target set E2, E3 and onwards. So, in order to get the E3, we have to consider a vector G2, which is nothing but H2 minus inner product of H2 and E1 multiplied by E1. So, inner product is nothing but a, since it is nothing but a scalar multiplier, we can formulate this vector as in this particular form. Now, what we can do? We take inner product of this equation with respect to vector E1. So, if we do that, this becomes inner product of G2 and E1 is equal to inner product of H2 and E1 minus inner product of H2 E1 E1 with E1. So, this becomes H2 inner product of H2 and E1, and in this equation H2 and inner product of H2 and E1 is nothing but a scalar, and if we remember the property of the inner product, that it is, if it is inner product of alpha x and y, it should be, where alpha is a scalar multiplier, then this should be alpha times inner product of x and y. So, we take this inner product, this scalar multiplier H2 E1 out of this, and this becomes inner product of E1 and E1, and inner product of E1 and E1 is nothing but the norm of E1 this is nothing but the norm of E1, and we have already ensured that norm of E1 is equal to 1. So, therefore, this value will be equal to 1. This will be inner product of H2 and E1 minus inner product of H2 and E1. So, these two scalars are identical and opposite in sign. So, that will be equal to 0. So, this simply indicates that the inner product of vector G2 and E1 will be equal to 0. So, if you remember the last class, if that is the condition, then we can come to a conclusion that G2 and E1 are orthogonal to each other. This simply indicates that G2 and E1 are orthogonal to each other. So, we get the second vector of the target set E, but we cannot ensure at this point of time that G2 and E1 are orthogonal, that is fine, but G2 is not orthonormal. We have to make the norm of G2 to be 1 to make it a orthogonal orthonormal set. So, the next element of the target set E2 is nothing but G2 divided by norm of G2. So, this ensures that the norm of E2 is equal to 1. We are doing this to ensure norm of E2 is equal to 1. So, now E1 and E2 constitute an orthogonal and at the same time orthonormal set of vectors. So, we have already obtained two elements of our target set. Next one is to get E3. We would like to obtain the next element of the target set. For that, we define G3 as H3 minus inner product of H3 and E1 minus inner product of H3 and E2 multiplied by E2. We consider this vector G3 is equal to H3 minus a scalar multiplier with respect to E1 minus another scalar multiplier with respect to E2. But this multiplier is nothing but the inner product of H3 and E1, and this multiplier is nothing but inner product of H3 and E2. Now, we take the inner product of this equation. Now we will be saying that G3 will be orthogonal to E2. In order to prove that, we have to take the inner product of this whole equation, let us say this equation number A with respect to E2. If that inner product turns out to be 0, then we can come to a conclusion that G3 is orthogonal to E2. So, we take inner product of equation A with respect to E2. So, this becomes inner product of G3 and E2 should be is equal to inner product of H3 and E2 minus inner product H3 E1 and E2 minus inner product of H3 E2 and E2. Now, again we will be utilizing the properties of the inner product, that inner product of alpha x and y is equal to alpha and multiplied by the inner product of x and y, where alpha is a scalar multiplier. Again, inner product is always a scalar, this is a scalar multiplier, this is a scalar, another scalar multiplier. So, they can be taken out of this bigger inner product sign. So, if we do that, this becomes inner product between G3 and E2 should be equal to inner product between H3 minus E2 minus inner product of H3 and E1 is a scalar. So, therefore, it will be out of the larger inner product sign. So, this will be inner product between H3 and E1 multiplied by inner product between E1 and E2 minus H3 and inner product of H3 and E2 being a scalar will be taken out, and this will be inner product of E2 and E2. So, let us see what we get. This is inner product of H3 and E2 minus inner product of H3 and E1, and we have already said and proved that E1 and E2 are mutually orthogonal to each other. So, therefore, inner product of E1 and E2 will be equal to 0, this will be equal to 0 minus inner product of H3 and E2, and what is inner product of E2 and E2? It is nothing but the norm of E2, and we have already proved earlier that E2 is defined in such a way that the norm is 1. So, this will be unity. So, what we get? We get inner product of H3 and E2 minus inner product of H3 and E2. these two being scalar and opposite in sign, they will be simply cancelled out and this will be equal to 0. This proves that G3 and E2 are orthogonal to each other, but it does not prove, it does not confirm that norm of G3 is equal to 1. So, it is still now it is an orthogonal set, but not an orthonormal set. So, we have to make G3, we have to normalize G3 to make its norm 1. So, for that we define E3 such that E3 is nothing but G3 divided by norm of G3. So, this ensures that E3 has a norm 1. Now, so therefore, E3 is directly derived from G3, E3 and E2 will be mutually orthogonal to each other. So, E3 and E2 are now orthogonal to each other. We have already proved that E1 and E2 are orthogonal, E2 and E3 are orthogonal, therefore, E3 and E1 have to be orthogonal. So, now we can say that we obtain the target set E E1, we have obtained E1, E2, E3 from H1, H2 and H3, and this set is basically orthogonal and orthonormal set. For kth space, this whole analysis can be extended and this can be generalized as you will be obtained the kth vector as G of the target set as Hk multiplied by summation of this I is equal to 1 to k minus 1 inner product of Hk Ei multiplied by Ei. So, using this generalized formula, one can obtain, keep on getting the vectors G1, G2, G3, G4, G5 up to Gk, and then make Ek as orthonormal by defining this. So, you will be getting from Hk set of independent vectors, you will be getting Ek set of independent vectors which are orthogonal as well as orthonormal. So, this is the principle of Gram-Schmidt orthogonalization. So, using this technique one can get a set of from any set of independent vectors into an orthogonal and orthonormal set of vectors. Next, we will take up an example to illustrate the Gram-Schmidt orthogonalization technique and the different calculations those are involved here. So, next example we take to illustrate these techniques. So, this is nothing but illustration of Gram-Schmidt orthogonalization technique. We consider 3-dimensional real space and we consider 3 vectors u1 as 1, 2, 3, u2 as 2, 3, 1, u3 as 3, 1, 2, and we check whether these 3 vectors constitute an independent set of vectors or not. in order to test that, we evaluate the determinant forming by the elements of these vectors. So, it will be 1 2 3, 2 3 1, 3 1 2. So, it is 3 into 3 determinant. So, just open up this determinant. If you open up this determinant, this becomes 1 multiplied by 3 1 1 2 minus 2. So, this will be 2 3 1 2 plus 3, this will be 2 3 3 1. As next step, do the internal calculations. So, this will be 2 into 3 6 minus 1 minus 2, 2 into 2 4 minus 3 plus 3 multiplied by 2 into 1 2 minus 3 into 3 9. So, it will be 1 into 6 minus 1 5 minus 1 into 2. So, it will be 2, this will be minus 7 into 3. So, it will be minus 21. So, this will be minus 7 minus 21. So, it will be plus 7 minus 21. No, this will be 5 minus 2 is 3, 3 minus 21. So, it will be minus 18. Of course, these will be not equal to 0. So, therefore, since the determinant is not equal to 0, the set constituted by u1, u2 and u3 form the independent set of vectors. Now, of course, if you look into the values, if you take the inner product of these vectors, let us say u1 and u2, the inner product will be 1 into 2 plus 2 into 3 plus 3 into 1. So, this becomes 2 plus 6 plus 3 is equal to 11. So, this is of course not equal to 0. That means, although u1, u2, u3 are independent to each other, but u1 and u2 and u3 they do not form an orthogonal set of vectors. So, now we have to take recourse to the Gram-Schmidt orthogonalization technique and evaluate and get from u1, u2, u3 set, we will be getting e1, e2, e3 set such that e1, e2, e3 will be mutually orthogonal and orthonormal. So, the first element we are targeting at is e1. e1 is nothing but u1 divided by norm of u1. So, u1 is 1 2 3. So, it will be 1 2 3 and norm of u1 will be nothing but root over 1 square plus 2 square plus 3 square. So, it will be 1 over root over 1 plus 4 plus 9 1 2 3. So, this will be 1 over root over 14 1 2 3. So, this gives this e1 is the first element of the first vector of your target set E. So, e1 is nothing but 1 over root over 14, 2 over root over 14, 3 over root over 14. Next, we go for the second element, second vector of this set, that will be given by G2. G2, if you remember, this is nothing but U2 minus inner product of U2 and E1 multiplied by E1. And what is U2? If you remember, U2 is nothing but 2 3 1. So, let us first calculate this inner product between U2 and E1 as 1 by root over 14 into 2. So, it will be 2 divided by root over 14 plus 2 divided by root over 14 into 3 plus 3 divided by root over 14 into 1. So, it will be, if we take root over 14 as common, this becomes 2 plus 6 plus 3. So, this becomes 11. So, 11 divided by root over 14. So, that is the inner product of U2 and E1. Now, we are in a position to formulate the value of the vector G2, and the G2 now becomes U2 minus inner product of U2 and E1. So, this becomes 231 minus 11 by root over 14 multiplied by E1, and E1, if you remember, this is 1 over root over 14, 1, 2 and 3. So, this becomes 231 minus 11 by 14, 1, 2, 3, and we are in a position to get the elements of the vectors G2. This will be 2 minus 11 by 14, next will be 3 minus 2 into 11 by 14, that is 22 by 14, next will be 1 minus 11 by 14 into 3, so it will be 33 by 14. So, you can simplify this equation and this becomes 17 by 14, 20 by 14 and minus 19 by 14. So, we get the vector G2 and then we make it orthonormal. So, therefore, we make its norm as to be 1. So, we evaluate the norm of G2, this becomes 17 by 14 square of that plus 20 by 14 square of that plus minus 19 by 14 square of that. So, this becomes 289, 196 plus 400 by 196 plus 381 divided by 196, and the whole thing becomes 1070 divided by 196, and norm of G2 is now is nothing but 10 root over 1070 divided by 14. So, we are in a position to get the second element of the target set E2 as G2 divided by norm of G2, and this will be root over 1070 divided by 14, 17, 20 minus 90. So, that gives the second element E2 of our thing, and now we can test whether E1 and E2 are orthogonal to each other or not. So, it is sure that they are orthonormal. So, if you take the inner product of E2 and E1 and E2, it will be, so this is E2, and if you write E1 just next to it, so this becomes 1 over root over 14, 1, 2 and 3. So, if you evaluate this one, this will be root over 1070 divided by 14 into 17 into 1 over root over 14 multiplied by 1 plus root over 1070 by 14 multiplied by 20 multiplied by 2 root over 1 by 14 minus root over 1070 divided by 14 multiplied by 19 plus 3 multiplied by 3 divided by root over 14. If you take root over 1070 by 14 and 1 by root 14 common, you will be getting 17 plus 40 minus 57. So, 17 plus 40 is 57, 57, 57 0. So, this whole thing becomes 0. So, this becomes 0. So, E1 and E2, the inner product between E1 and E2 becomes 0. That means, E1 and E2 are orthogonal, and since each of them is orthonormal, they are orthonormal as well. Therefore, these two elements E1 and these two vectors E1 and E2 are the first two members of my target set E. Next, we will be considering the calculating the third vector G3, and if you remember, G3 is nothing but U3 minus inner product of U3 and E1 multiplied by U1 minus inner product of U3 and E2 multiplied by E2. So, if we just for the sake of easiness to follow up, we just write down the values of these three vectors. U3 E1 is 1 over root over 14, 1, 2, 3, and E2 is root over 1070 divided by 196, 17, 20, minus 19. So, we first evaluate the inner product of U3 and U1. Next, we evaluate the inner product of U3 and E2. So, things becomes simplified later on. So, inner product of U3 and E1 is nothing but 3 multiplied by 1 over root over 14 plus 1 multiplied by 2 over root over 14 plus 2 multiplied by 3 over root over 14. So, this becomes 11 by root over 14, and inner product of U3 and E2 can similarly be calculated as root over 1070 divided by 196 multiplied by 51 plus 20 minus 38. So, U3 and E2. So, this multiplied by this plus 1 multiplied by 1070 divided by 196 into 20. Likewise, so you will be getting this as 33 root over 1070 divided by 196. Okay. So, we will be in a position to get G3 now more accurately. So, G3 will be U3 is 3, 1, 2 multiplied by 11 by 14, this one inner product between U3 and E1, 11 by root over 14 multiplied by 1 over root over 14, 1, 2 and 3 minus inner product of U3 and E2, this will be 33 root over 1070 divided by 196, and this one will be 17, 20, minus 19 multiplied by, it has root over 1070 divided by 196. So, this becomes 312 minus 11 by 14, 1, 2, 3 minus 33 into 1070 divided by 196 square is into 17, 20 minus 19. So, now we should get into the decimals and simplify this equation. So, G3 now becomes 312 minus 0.785, 1.571, 2.357 minus 15.62, 18.38 minus 17.46, and this becomes, after simplification, 13.41 minus 18.95, 17.10. So, that is the third vector G3, which is orthogonal to each other with E1 and E2, but to make it orthonormal, we have to normalize G3 by this formula G3 divided by norm of G3. So, this will be 1 over root over 13.41 square, this minus will be gone when the square is taken, 18.95 square plus 17.1 square, and this will be minus 13.41 minus 18.95 17.10, and after taking the square root, this becomes 1 over 28.83 minus 13.41 minus 18.95 17.1, and you will be getting as minus 0.465 minus 0.657, and this will be plus 0.593. So, we get the elements of the target set, vectors of the target set E1, E2 and E3, where E1 and E2 are mutually orthogonal, E2 and E3 are orthogonal, E3 and E1 is orthogonal, and each of them will be having a norm 1. That means, we are getting an orthogonal, orthonormal, set of vectors out of independent vectors U1, U2 and U3. So, this gives the demonstration how Gram-Schmidt orthogonalization technique is utilized in order to make the basis set vectors into orthogonal and orthonormal set of vectors. Okay. So, next we go to the topic of contraction mapping, and contraction mapping is a very important technique, mathematical technique, and maybe well utilized by the chemical engineers to analyze the unique steady state or unique solution to a problem. So, therefore, this is very important technique. All the chemical engineering processes are depending on the basically the quality of the processes will be evaluated. What is the product quality you are going to get? Suppose we are having a process, there are certain inputs into the system, and the system gives some outputs. Now, the product or the quality of the output becomes very important. For example, if we talk about a polymerization reaction, there will be a polymerization reactor where the polymerization reaction is going on. We are going to have certain reactants getting into the systems, maybe monomers and some of the copolymers, or some of the catalyst may be getting into the system, and what is the output of the system? From the output, we are going to get polymers of various grades. Now, grading of these polymers, the quality of the polymers are extremely important. For example, these polymers will be having certain properties. The importance and the utility of these products will be evaluated by the properties. For example, the polymer properties are evaluated in terms of certain physical properties. For example, melt flow index, that is directly related to the viscosity of the product, melt flow index, stress exponent, things like this. Now, all these properties have to be evaluated, and it has to be, and generally these properties are desirable within a narrow range. So, if for example, if we going to get a melt flow index in the range of 8.5 to 8.8, that will be grade 1 polymer. If we are going to get the range of this particular property between 0.90 to 0.95, that will give me another grade of polymer, and each of such products will be having its specific utility and use. Now, if we cannot control these qualities of the product, then the whole batch will be spoiled, and you will be wasting huge amount of manpower, energy, and material and money, of course. So, in order to get that, we would like to operate the whole system in a steady state, and that steady state has to be a unique steady state. There may be a mild fluctuation in the real time operation, but the steady state has to be a unique one. We should not land up with a multiple steady state, where in one case we are going to get a product quality of let us say of specificity between a range R1, and in another steady state we are going to get another product quality in the range R2, where R1 is desirable and R2 is not desirable. So, therefore, the identification of the operating conditions which will make your system having a unique steady state is extremely important for the chemical engineers. There exists a fixed set of operating conditions which will give me a unique steady state or a unique fixed point, we call it mathematically, in a chemical engineering operation. So, determination of steady state and whether that steady state is unique steady state for the, and what are the conditions of the operating parameters that will ensure that the steady state is a unique steady state is very important for chemical engineering, for the chemical engineers to control the chemical engineering processes. So, contraction mapping is one such techniques which mathematically can tell you what will be the condition of the operating parameters such that you are going to land a steady state, and that steady state is ensured to be a unique steady state. So, we start with the contraction mapping. So, the utility of this technique is to identify the conditions for which a unique steady state is obtained. What we will do, we will have the formulation of the mathematical formulation of this contraction mapping, and we will look into the theory of this development, and then we will be taking off a couple of examples, maybe 4 or 5 examples to of different chemical engineering system to demonstrate the use of contraction mapping in order to identify the conditions for having a unique steady state. Okay. Consider, let us look into the mathematical development and the mathematical analysis involved behind this contraction mapping technique. Consider the function f x, and domain of f x is a real line. This is a real line. So, we are working in real domain, and range of f x is also a real line. Now, X is a metric space in this domain where a metric D is defined. Now, if this is the system, then if we have a relationship in this form, f x naught is equal to x naught, if we can mathematically describe a chemical engineering system in this form, f x naught is equal to x naught, then x naught is termed as a fixed point of map F. So, if in your chemical engineering system we write down the mathematical formulation to mathematically express this system, and if it is ultimately in this form x naught is equal to f x naught, then x naught is termed as a fixed point to the map F. So, next we look into the theorem of contraction mapping. The theorem goes like this: F is a contraction map if the metric d of f x and f y is less than k times metric between x and y for k lying between 0, 1, 1. So, we should call the map f as a contraction map if the metric between f x and f y is less than equal to k times metric between x and y, where k is a fraction. Then we call this, if this relationship is obeyed, then this fraction this map f is called a contraction map. Now, next is if this relation holds for all x and y in the complete space, then f x has a unique fixed point. Now, this has to be, so this is a definition of contraction map. If metric between f x and f y is less than k of k times metric between x and y, where k is a fraction. If this relation holds for every x and y in the complete space, then f x has a unique steady state. Now, what happens if this relation does not hold? If the above relation does not hold, then f x may have more than, not unique, more than one fixed point or none at all. So, if this relation does not hold, that does not mean that it will be having more than one fixed point. It may not have any fixed point at all, but if this relation holds, it is ensured that you will be having a unique fixed point. Okay, let us go into the proof of this theorem. The proof goes like this: let x naught is an element in the space and we define a sequence. Let us define a sequence such that x n plus 1 is equal to f of x n. So, therefore, x 1 is nothing but f of x naught, x 2 is nothing but f of x 1, likewise. Now, f is a contraction map if metric between x 2 and x 1, which is nothing but x 1 is nothing but f of x 1, metric between f of x 1 and metric between x 1 and x 2 and x 1. So, x 2 will be nothing but f of x 1 and x 1 is nothing but f of x naught. is less than equal to k times, it is basically less than k times metric between x 1 x 2. So, we are assuming that F is a contraction map. In that case, D of metric between x 2 and x 1 should be nothing but identically equal to a metric between x 2 is nothing but f of x 1 and x 1 is nothing but f of x 0. But if F is a contraction map, then this relationship must be holding good, that is metric between f of x 1 and f of x 0 should be less than k times metric between x 1 and x 0. Okay. Similarly, we can have metric between x 3 and x 2 should be less than k times metric between x 2 and x 1, identical logic. So, metric between x 2 and x 1 is less than k times metric between x 1 and x 2. So, this should be, by combining these two, we can write this will be nothing but k square d times metric between x 1 and x 0. With the identical logic, we can go to the next step, and write metric between x 4 and x 3 should be less than k times metric between x 3 and x 2. We have already proved that metric between x 3 and x 2 should be less than k square metric between x 1 and x 0. So, this will be less than k cube metric between x 1 and x 0. Therefore, we can continue like this and we can get a generalized equation metric between m plus x m plus 1 and x m should be less than k to the power m d metric between x 1 and x 0. Now, we will look into the triangle inequality of the metric property. Go to the property of metric. This property says that metric between x and y should be less than metric between x and z plus metric between z and y. Now, we assume m much greater than n, we can, using this triangle rule of metric, we can write down metric between x m and x n should be less than equal to less than metric between x m minus 1 plus metric between x m minus 1 x m minus 2 plus up to metric between x n plus 1 and x n. So, we have already found out that metric between x m and x m minus 1 by this relationship, it will be just to change the indices. So, it becomes k to the power m minus 1 metric between x 1 and x 0. This will be nothing but k to the power m minus 2 metric between x 1 and x 0 up to k to the power n metric between x 1 and x 0. So, in a sense, we will be getting a series type of equation out of this, and we further proceed and simplify this equation. So, metric between x m and x n can now be written as metric between x 1 and x 0, that is a scalar. So, it has to be taken common and we can write it down as k to the power m minus 1 plus k to the power m minus 2 up to k to the power n. So, this becomes a series. So, metric between x m and x n can be written as metric between x 1 and x 0, and this series can now be we can take k to the power n as common. So, this becomes 1 plus k plus k square plus k to the power m minus n minus 1, we take k to the power n as common. So, this becomes k to the power n 1 over 1 by minus k d to the power metric between x 1 and x 0. Now, as n increases, n goes up to infinity, and k being a fraction, k is less than 1. So, k to the power n goes to 0, as k lying between 0 and 1, it is a fraction. So, as n tends to infinity, k to the power n tends to 0. So, therefore, metric between x m and x n is much less than epsilon for sufficiently, where epsilon is a small quantity, quite small, for sufficiently large n. Therefore, this, since it is true, this relationship is true for any arbitrary value of m and n. So, the sequence we are talking about is a Cauchy sequence. Thus, the sequence is a Cauchy sequence, and x n converges. So, therefore, we will be since it is a Cauchy sequence, the value will be, so the sequence is a converging sequence and it will be converging to a point, and that point is a fixed point. So, we have already proved that using contraction mapping, that for the function f, metric between f x and f x 1 and f x 2, f x m and f x n for sufficiently large values of m and n, if it is less than k times metric between x 1 and x 0, it will be converging to a fixed point x naught, and that proves the contraction mapping. Using contraction mapping, how one will be getting a converging sequence. Next, we will be getting a the whole sequence will be converged to a fixed point, but next we will be proving that this fixed point is a unique fixed point. Once we prove that, then our whole proof will be complete. Then we can go to a proper appropriate chemical engineering application. Okay, so that I will take up in the next class. Thank you very much for your kind attention.